Hello everyone, my name is Wentao. I'm here to give a presentation for my thesis project, Device-Level Power Electronic System Emulation for Hardware-in-the-Loop Applications. First, I will thank my supervisor, Dr. Venkata for his insightful instruction for this research. This presentation contains 4 sections. Section 1 is Introduction. Section 2 is Physics-based Device Model Hardware Emulation. Section 3 is Case Studies, Experimental Results. Section 4 is Conclusions. There are several motivations for this work. First, an accurate physics-based power electronic device hardware emulation has yet not been reported in literature due to its huge computational burden. Second, high-fidelity device-level modeling does have its benefits, especially to the current trend to miniaturize power electronics in various applications whose performance can be influenced by high-frequency switching devices. Third, detailed device-level models would provide insight into high-frequency effects such as device stresses, parasitics, electromagnetic interference, noise issues, and their suppression. Hardware-in-the-loop simulator, HIL simulator, is an embedded hardware system which connects to the external system and the test by various I/O interfaces. HIL simulators have advantages low cost and of excluding the possibility to damage the physical devices and the unexpected transient conditions. HIL simulators have been gaining popularity in many industries such as automotive, aerospace, and electric power systems. HIL simulators can be classified into controller HIL and power HIL. There are several advantages of FPGAs for HIL applications. First, FPGAs are inherent parallel hardware architecture, allowing an ultra-low latency realization of complex algorithms. FPGAs have very large capacity devices comprised of millions of logic building blocks to provide substantial hardware resources. FPGAs have mature and advanced design and development tools for rapid prototyping, allowing users the choice of architecture, VHDL or Verilog, or schematic design entry methods. FPGAs have fast clock speeds and high-speed transceivers to communicate with external devices. FPGAs are reconfigurable and allow firmware to be reprogrammed. The typical structure of FPGA is a two-dimensional symmetrical CLB arrays. A CLB contains 2 slices. Each slice contains lookup table and flip-flops. FPGA design flow begins with design specification and HDL coding. Also, behavioral simulation should be performed as well as synthesis. Implementation contains map, place, and route. Also, stated timing analysis should be performed. After all these have been done, generated bitstream file should be downloaded to the FPGA board and to verify. There are several challenges to emulate device-level models. First, the emulation needs to solve typically a large set of coupled nonlinear equations. Second, the emulation should be performed within a time step of a few nanoseconds to capture the high-frequency device behavior. Third, the emulation demands to use a variable time step for computational efficiency. Most importantly, circuit size for practical application requires to model enough nonlinear switches. The hardware design begins with the power diode module. As can be seen from the figure, the physics power diode model contains 5 major phenomenological characteristics, including reverse recovery, forward recovery, emitter recombination, contact resistance, and junction capacitance. The powered model should be discretized using trapezoidal rule as well as linearization. Reverse recovery, emitter recombination, and junction capacitance are modeled as its related dynamic conductance and equivalent current. Especially, the forward recovery is modeled as a nonlinear resistance. After that, those conductance and equivalent current combine a 3x3 conductance matrix and the current vector of diode. The detailed structure of the power diode module is shown in this figure, which contains 3 stages. Stage 1 contains a junction limit unit, which is used to limit the PN junction voltage during successive Newton iterations. Stage 2 contains 4 units, which runs in parallel. Stage 3 receives the calculated dynamic conductance and equivalent current and nonlinear resistance to combine the 3x3 conductor matrix and equivalent current vector of the diode. The detailed structure of the reverse recovery unit is shown in this figure. Calculation for the current is shown in the upper square. As can be seen, the calculation for the current and the conductance run in parallel. Especially, the purpled area has the resources which contribute to both the calculation of current and conductance. The value in the yellow boxes are the constant signals which have been pre-calculated offline in order to reduce the whole latency of the design. Now we come to the hardware design of the IGBT module. From Figure A, the IGBT contains a inner BJT, which has its base current fed by the MOSFET. The BJT and MOSFET, as well as the capacitance, is converted to the current, nonlinear current, and capacitance shows in the right figure, analog equivalent circuit of IGBT. Similarly, the IGBT module should be discretized using trapezoidal rule, and and be linearized. Those current and capacitance are modeled as its related dynamic conductance and equivalent current. Then those values combine a 5 by 5 matrix of conductance matrix of IGBT as well as equivalent current vector. This figure shows the detailed structure of the IGBT hardware module on FPGA. It contains 4 stages. Stage 1 contains 2 junction limit units and a charge limit unit, which are used to limit the p-n junction voltage and charge variation between successive Newton iterations. Stage 2 contains 8 units which run in parallel. Especially, the largest anode, base and collector currents units contain several subunits which interconnect with some capacitor units. These units should be triggered at the right time. In stage 3, there are 2 units, avalanche multiplication current unit and the capacitor CMOS unit, which run in parallel. Stage 4 receives the calculated dynamic conductance shown in the blue, as the blue arrows, and the equivalent current shown as the yellow arrow, and they are combined as a 5 by 5 conductor matrix and the equivalent current vector of the IGBT. In the hardware structure of the IMOS unit, there are 3 comparators and 3 layers of multiplexers, which are used to select the temporary results from the calculation of 3 conditions and send them to the output. In the architecture of power converter hardware model, the power diode hardware module and IGBT hardware modules are canned in interval 2. Also, there is a linear component module. These modules are used to calculate its related conductor matrix and equivalent current vector, which are in turn transferred into the power converter conductor matrix and current vector module to combine the conductor matrix and the current equivalent current vector of the whole power converter hardware model. Then a fast parallel Gauss-Jordan linear solver is applied to calculate the node voltage of the circuit. In interval 1, the current time step is decided by the Newton iteration times of the last time step calculation. Also, the PWM switching signals is calculated too. Interval 3 is used to generate the output values, which are in turn sent to DAX. The detailed structure of variable time-step control module and variable time-step output module is shown in these slides. There are 3 layers of multiplexer, which are used to calculate the current time step based on the Newton iteration times of the last time step calculation. In the variable time step output module, the current time step is divided by the minimum time step to generate an integer value, which are used to decide the repetitive times of the prospective output values to be stored in the FIFO registers. Especially, there is an output pace control unit, which is used to control the refresh rate of the FIFO registers to the output. This slide shows the detailed structure of the parallel Gauss-Jordan linear solver. This linear solver is featured by parallelism in both forward elimination and backward substitution at the cost of using extra hardware resources. The pivot rating is set to as fast as 2 clock cycles each step. The experimental setup is shown in the right figure. The Zinc Vertex 7 FPGA is applied, which is connected to the DAC boards by FMC connectors. The DAC boards in turn connects to the oscilloscope. The test circuit is a DC-DC buck converter. From the hardware resource usage table, we can see most of the hardware resources contribute to the design of the IGBT. This slide shows a 5-dimensional discrete time linearized system equation of the DC-DC converter. This slide shows a device-level DC-DC buck converter model, which is built on Sabre. These slides show the emulation results, which are compared with Sabre. The upper figures are from oscilloscope. The lower figures are from Sabre. The slides show the emulation results. Especially, the right one is a transient figure. The switching time is marked out in the oscilloscope results. These three figures are also transient simulation results. As can be seen, all the emulation results show good agreement with the results on Sabre. These figures shows the power dissipation of the switching devices, IGBT and diode, with the increasing of the switching frequency. As can be seen, FPGA and Sabre agreed closely at low and high frequencies. IGBT switching losses and diode reverse recovery loss rose fast. However, IGBT conduction loss increased slowly. Diode conduction loss remained almost constant. This is another test circuit, a two-level DC-AC converter. The two-level DC-AC converter is divided into three identical nonlinear sub-circuits. This three leg is connected to RL loads, which are temporarily treated as history current sources. The linearized system equation of the sub-circuit is shown in this slide. This slide shows a linear sub-circuit of the three-phase loads. The values of the shows in this figure can be calculated by a group of equations shows in this slide. This figure shows the device-level two-level DC-AC converter model, which is generated on Sabre. The steady-state results of the hardware emulation is shown in this figure, which are compared with Sabre results. The transient results of the hardware emulation is shown in this slide, which are compared with Sabre results. The left one is a power loss analysis figure. As can be seen from these figures, all of the results from the hardware emulation show good agreement with Sabre results. Conclusions. The concept of modularization is introduced to the physics-based device for power electronic circuit hardware emulation. Second, a complete complete description of the parallel IGBT and power diode hardware designs is presented. Also, the concept of variable tensor strategy is introduced to the field of Hill simulation. A fast parallel Gauss-Jordan linear solver is designed in this project. Most importantly, validation is made using Sabre, a sophisticated device-level commercial simulation software. Steady-state and transient results are observed as well as power analysis. At the end of this presentation, I would like to thank Synopsys for the donation of Sabre license during the course of the research from 2012 to 2014. That's all of my presentation. Thank you for listening.